So it is really my great honor to be awarded this prestigious Levi Civita International Prize. So I would like to thank the organizers, committees, members. Really, it's a great pleasure and honor for me. And also, it is a great pleasure to have an opportunity to give this talk. Fortunately, I received the award, the prize first, and then give a talk. If the order is inverted, then the committee might have changed the idea. But, anyway, so this title is not very correct. I say the recent topics in my research, not general. So this, I am from the Department of Mechanical Engineering and Science of Kyoto University. I dropped my name of my university, sorry, Kyoto University in Japan. And this is a collaboration with my former PhD students, Satoshi Taguchi and Tetsuro Tsuji, and some part, small part with François Gauss, mathematical part. But today I present only the numerical part. And I start with a very elementary, very elementary introduction to kinetic theory of gases, because I had no idea about the audience. Maybe I'm now afraid that I see many experts in the statistical mechanics and the kinetic theory. I hope it's okay. So what is kinetic theory of gases? Rarefied gas dynamics or molecular gas dynamics? This is modern name. As you know, the gas is an ensemble of many molecules. Probably you remember the number, Avogadro number, 6 times 10 to the 23rd, a huge number of molecules in 1 mole. And then they are moving very fast. The average speed of the molecules are like sound speed, 300 meters per second. And in addition, in ordinary gas, such as the air in this room, then they undergo very frequent collisions. And the mean free path, which is the average distance between two successive collisions, is 10 to the minus 6 centimeters, like this. So it flies very fast and collide in such a way. So many dramatic things are happening around us, but we don't see. We can perceive only the average velocity of the molecules. And so when we say that there is a wind of 5 meters per second, then this means that the average of the molecular velocity is like this. Okay? And the important concept is the velocity distribution of gas molecules, how the molecules are numbers of molecules are distributed according to the velocity. And in ordinary gas, with a frequent collision like the air in this room, the shape of the distribution is almost a Gaussian distribution, which is called Maxwellian distribution. And this is a form of Maxwellian distribution. So the V bar is the average velocity, and T is the temperature, and N is the number density, if you consider the unit volume. And so this is a schematic figure in 1D. So the velocity is, in general, it's 3D, but 1D figure is like this. And so the shape is like the bell-shaped distribution. And the V bar is the peak, this average. And square root of RT is corresponds to standard deviation. So the temperature determines the width of this distribution. And then the number density is a volume of here, below the curve. Okay? And in this way, when the collision is very frequent, these things, average velocity, temperature, and the number density determines this shape completely. Okay? This can change from point to point as time goes on. So this situation is called the local equilibrium. So that is the velocity distribution of the gas molecules are described by this equation, but the temperature, density, and the mean velocity changes depending on the time and position. So if you know this variation change, then you can completely describe the situation of the gas. And this corresponds to fluid mechanics. Okay? And so you handle only macroscopic variables. Okay? And you have partial differential equations for macroscopic variables. Then it's enough to obtain all the information. But in low density gas is like higher atmosphere or vacuum inside vacuum facilities, or gas in microscales, a very tiny micro machine. Okay, then the molecular collisions are not sufficient to form the local equilibrium, this Gaussian shape. So maybe the distribution of the gas velocity can be like this. Okay? So this deviation from the Gaussian or local Maxwellian or local equilibrium is roughly measured by the number called Knudsen number, which is defined by this equation, the mean free path of gas molecules divided by the characteristic length of the system. And as I said, the mean free path in the air of this room is very short, 10 to the minus 6 centimeters. So if you consider the system of this size, then the Knudsen number is 10 to the minus 7. It's practically 0. But in the low density gases, the mean free path can be very long. And in microscale systems, the denominator, the characteristic length can be very short. Therefore, the Knudsen number can take non-zero values. And in principle, it can take any positive values. And when it is infinitely large, then it is called free molecular flow. And you can completely neglect the effect of intermolecular collisions. And on the other hand, this limit, when Knudsen number going to 0, is called the fluid dynamic limit or continuum limit, where the gas is in local equilibrium and is delicate. So very close to local equilibrium, this corresponds to fluid dynamics. Fluid dynamics is supposed to be valid in this zone, very close to this limit. And but for general Knudsen number, the shape of distribution is not determined by this average velocity, temperature, and the number density. So it could be infinitely many possibilities to give same macroscopic quantities. So in that case, you have to handle the distribution itself. And the equation for the distribution itself is the celebrated Boltzmann equation, which Ludwig Boltzmann proposed in 1872. And and the molecular gas dynamics or rarefied gas dynamics is the gas dynamics for the distribution itself. And this is a more general gas dynamics, including the ordinary gas dynamics as a limit, like this. So in many fluid dynamicists think that the molecular gas dynamics is a very special field, but it is not true. It's a more general field. So this is one example which you can easily see the effect of deviation from local Maxwellian. So I will come back to this later. And this is a tomb of Ludwig Boltzmann in Vienna. If you magnify this, then he died in 1906 in Italy, in Duino, near Trieste. And here you see the equation. It's very rare that you see the equation on the tombstone. Okay, so S is equal to K log W, it's famous entropy. And but not the Boltzmann equation. Maybe it's too complicated to carve on the tombstone. So the Boltzmann equation is a very classical equation, but it has been an important equation in non-equilibrium statistical mechanics. It's a classical. And for instance, many books have been published on this subject, like Carlo Celcignani published several important books on this subject, including the is Ludwig Boltzmann, the man who trusted atoms from Cambridge University Press. And currently, the Boltzmann equation is the practical equation in rarefied gas dynamics and also microfluidics, and also the not very hot, steadily hot topic in statistical physics and applied mathematics. One good example is that Cedric Villani received the Fields Medal in the year 2010 because of his proof of nonlinear proofs of nonlinear random damping and convergence to equilibrium for the Boltzmann equation. Yeah. So this is from, I took this sentence from here. It's the homepage of the International Congress of Mathematicians in 2010. And this is one photo of Cedric Villani. And because here, you see, this is the reception at the conference dedicated to Carlo Celciniani in 2011, February, in Paris. And this reception was held in Italian embassy in Paris. And this is inside the embassy. And you see some familiar faces. And I was too bad. I cut the important face here. I'm very sorry for that. Okay, so a little more precisely, the velocity distribution function is, in general, the function of time t and position x and molecular velocity c. And its physical meaning, originally it's a probability density. But for application, we interpret that it is a mass density in a six-dimensional phase space. And namely, if you consider the small box dx dx around the point x and c in this six-dimensional phase space, then the molecular mass, well, molecular number. For application for single component gas, maybe it's better to use mass. The molecular mass in this small box at time t is described in this way. So this is a definition. And once you know the velocity distribution function, then all the macroscopic variables, quantities, can be obtained as a moment of a velocity distribution function. For instance, the density, mass density, is just the integral of f over the whole molecular velocity space, and flow velocity, fluid dynamic velocity, is the average of molecular velocity with this distribution f, and also temperature and stress tensor and heat flow vector you can define in terms of velocity distribution function. And the equation for this velocity distribution function is the Boltzmann equation. It's complicated. When there is no external force, it is usually written in the following form. And the left-hand side is very simple, but the right-hand side is very complicated. It's non-linear, and it contains five-fold integrals. And, but I omitted the details today. This is not relevant to my talk. And, but I wanted to note one thing. Since this is too complicated for practical applications, very often it's model equations are used. And maybe the simplest and most widely used model equation for the Boltzmann equation is the BGK model. So I will use this later. BGK model after Bartonella, Gross, and Crook. But the same equation was proposed by Belander in the same year, independently. And so in this model, the collision term is replaced by such a simple relaxation term. Okay? So it looks very simple, and in fact it is very simple. But concerning nonlinearity, it is much worse than the original Boltzmann equation, because this is local Maxwellian. The local Maxwellian contains the functionals of f inside the exponential. So it's a terribly nonlinear equation. But still, for practical computation, it is much easier. And this satisfies most of the fundamental properties of the Boltzmann equation. And also, I have to mention the conventional boundary conditions. So for the Boltzmann equation, you have to specify the velocity distribution function for incoming molecules from the boundary, in principle. or reflected molecules, namely Xi minus VW dot n positive. So VW is the local velocity of the boundary, and the n is the unit normal vector pointing into the gas. So this dot is a scalar product. So for specular reflection, the simplest boundary condition is a specular reflection. That just the incident molecules are reflected specularly. But it is too idealized and too singular in some sense. So more practical and simplest and most widely used boundary condition is a diffuse reflection. So here you assume that the incident molecules are summarized in a solid and then re-emitted after equilibrium with the boundary. So this is called the diffuse reflection. In this model, the velocity distribution of the reflected molecules are distributed according to the Maxwellian distribution with temperature Tw of the boundary, local temperature of the boundary, and velocity of the local velocity of the boundary. But you don't specify the density of the Maxwellian. Instead, you impose the condition that there is no net mass flux across the boundary. So this leads to the following expression of this sigma W in terms of the impinging flux. So this contains unknown function f. So it's a bit complicated. So there are more sophisticated models like Cecchiniani-Lampis model and some others, but here I only use this model. Okay, so much is the brief introduction to kinetic theory. And now, I consider the first problem. So this is not a problem for application. It's I'd say this is a fundamental problem. Sorry for that. So this is the convergence to equilibrium, case of collisionless gas. So convergence to equilibrium. So it's a very trivial problem, but an important problem. So you have a box, container with constant temperature, and you have a gas inside, and you disturb the gas at the beginning. Then if you leave the container for a long time, then the gas should approach the equilibrium distribution with the same temperature as the boundary. So it is physically it's clear, but mathematically it's a very difficult problem. And in fact, in the case of the Boltzmann equation, if you assume the Boltzmann equation for the gas, it's a difficult problem. And this is turned to equilibrium. So many mathematicians consider this problem. And so one of the important contributions is the work by Debrett and Villani. And so they considered the specularly deflecting boundary in the box or periodic box, and then they showed that the F distribution function approaches final Maxwellian faster than any inverse power of time. Okay. So here the final Maxwellian is different from the previous one. So here the temperature of the Maxwellian is the same as the boundary, but for these boundaries, no information from the boundary. Therefore, the temperature is determined from the energy conservation. Okay, so density and the temperature are determined from the initial condition by mass conservation and energy conservation. And instead, in this case, energy is not conserved because of this diffuse reflection or some other kind of boundary condition. So only the mass is determined from the initial condition because of mass conservation. And maybe more recently, the exponential decay has been proved, I think, by I was told, I have never checked this, but I was told that in the paper by Galdani, Mishura, and Moreau, they proved exponential decay for periodic boundary condition. And but also an important thing is that later the Cedric Villani extended his proof to the case of diffuse reflection. The boundary condition that I explained. And also the same is true in the diffuse reflection case. So here the final Maxwellian is the Maxwellian that I showed. the temperature is the same as the temperature of the boundary. So he was able to prove this. Okay. And but I was interested in what happens when there is no molecular collision. Okay. So here, suppose that you have a collisionless gas, very rarefied, and then you put it in a box, then you wait for a long time. Then again, you should have a final Maxwellian, the same as before. And in fact, it was proved mathematically, rigorously, by Alkid and Nouri. So the convergence, this convergence. And, but they didn't mention anything about convergence rate. So we expected that the approach to equilibrium is very slow in this case, because only the interaction with the boundary summarizes the gas. Okay. So then my guess was like this: with the appropriate norm, the difference decreases like inverse power of time, and this d is a dimension of the box. Okay. So then we want to confirm this numerically. We wanted to give some pieces of numerical evidence for this, and we did some numerical simulation. And since the Boltzmann equation now is collisionless, the highly rarefied gas, the effect of collision can be neglected. So the Boltzmann equation reduces to such simple free transport equation. So it's very simple. You know, all of you know immediately the general solution of this, namely, F is constant along the characteristic line. Okay? So, therefore, the numerical solution is very simple. But you need a very careful computation because we have to handle the very small quantities. So just let me jump to the result. I omit the method of solution. And here, 1D box. 1D box means that you have infinitely wide plates, two plates, kept at the temperature Tw. I put tilde to indicate dimensional temperature. And then you assume that the physical quantities are independent in y and z direction, only depends on the x direction. So this is 1D box. And so I chose a very simple initial condition, which is a Maxwellian distribution, but only the temperature is different from the temperature of the boundary. So there are some results. The 0.5 is you put a cold gas, then it is heated with a boundary, and when it is 2, then you put a hot gas, and then it is cooled down by the boundary, like this. Then so here is the time evolution of the temperature. The 1 is a final temperature Tw, because it is normalized by Tw, so its final destination is 1. So T minus 1 goes to 0. This is time evolution with a double logarithmic plot with base 10. And so after some time, all the curves with different initial temperature tends to approach a straight line. And if you measure the gradient of these curves, then it tends to approach -1. So this means that temperature decays like this. So this is at this point. And so for other points, the behavior is the same. So this gives some. So here, the computation has been performed to a very long time. This is 10,000 in some appropriate unit. So and then we have to handle very small quantity, 10 to the -4 and so on, fifths. So you need a very careful computation. Although the computational method is very simple. And so this table gives this final gradient in these curves for various things. This is temperature. So with different initial temperature, you see most of them goes to almost 1. So here is minus. So this means that gradient goes to -1, and this relative entropy goes to -1, and the L1 norm of the difference goes to -1. But density and velocity decays faster. But anyway, this is at point 0.2 and time 10,000. And the other points, the behavior is the same. And so this gives some pieces of numerical evidence that shows that the decay is something like that, with d equal 1. And But the decay, the process of this decay, I have to, sorry, I take off my jacket, and then I have to change the position of this machine. Okay. So now I show the behavior of how the initial distribution approaches the final distribution in the collisionless case. So I show the marginal of the f. So here, the f is integrated over the two components of the velocity, molecular velocity, parallel to the boundary. So it's marginal is a function of time t and position x and molecular velocity cx, x component. And the first movie shows the time evolution of the velocity distribution function at this point, center. And next one, this point, close to the boundary. Okay, so this black curve already modified here. The black is initial distribution, high temperature, temperature 2. And the final one is a low temperature, temperature 1. So the approach is like this. This is not trivial. So it takes a long time because the slow molecules never interact with the boundary. And finally, there are molecules with zero velocity. So it never goes to the maximum. So if you measure the distance with say, L infinity norm, then it does not make sense. And in this position, it is close to the boundary, but not symmetric. So like this, it is interesting. So before computing, we never imagined. So, and also 2D, we have computed 2D and 3D boxes, but we are cheating. The 2D box is just a cylinder. Because essentially, if you start from a uniform initial condition, then it's a cylindrical symmetric, so it is practically 1D. But the effect is 2D. And in the 3D box, we consider only sphere with a spherically symmetric, or more precisely, uniform initial condition. Then also, it is practically 1D, but the effect is 3D. Then we confirmed, at least in these very limited cases, but we are able to present some numerical evidences which supports such a decay rate with D, the dimension of the box. And somehow this slow decay is caused by the long memory effect caused by very slow molecules. And but the interesting long memory effect caused by the recolliding molecules when the boundary is moving was proposed by Caprino, Marchiolo, and Pugliese here. And then some subsequent papers. So they discuss this long memory effect. And also, concerning this decay in collisionless gas, we did some numerical, theoretical work. But in this paper, we are not able to give a sharp estimate. But recently, Taiping Liu and his co-workers were able to show this in a spherical geometry. They used the probabilistic approach, the central limit theorem, and they took the Shishen-Yu's method. And another interest is that what happens when there is a collision. So as I said, the Cédric Villani proves that the approach is faster than any inverse power of time. So we wanted to confirm it. And so we use the VGK model that I showed because it is complicated. If you use the Boltzmann equation, we can use the Boltzmann equation, but we cannot describe the singularity with Boltzmann equation. With VGK, we can do that. So we use the VGK model, and the initial temperature is the same as before, twice of the world temperature. And the time evolution of the temperature and L1 norm of the velocity distribution function at the center. So when the constant number is large mean free path, decay is slow, but as constant number becomes small, then decay becomes very fast. And this is a semi-logarithmic plot. And the decay, this graph approaches a straight line. So this means that the decay is something like exponential. And this coefficient changes depending on the constant number. And as constant number becomes small, then the decay becomes sharp, rapid. But after constant number 1, then it started increasing. And the constant number 0.01, the curve is like this. So this is consistent with the mathematical theory, but one point that this is the velocity distribution function in that case. So still there is a collision, but still there is a discontinuity. It is not so large as a collisionless case, but still you have discontinuity, and it propagates. So and the Milanese proof assumes the existence of smooth solution of the Boltzmann equation. But in this case, the solution is not smooth. So in this case, this is outside of the scope of this Milanese proof. Okay, so now I move on to the second subject. The first subject is really fundamental, not application. I'm sorry for that. The radiometric, this is a little more application, but not very much, sorry. So I said that there is an effect of, if you want to see the effect of deviation from local Maxwellian, local equilibrium, then this is one example. This is a Crookes radiometer, which was invented by the chemist William Crookes, British chemist William Crookes, in 1874, 2 years after Boltzmann equation. And maybe most of you have seen this. You have a glass bulb, and inside the bulb there are usually four vanes suspended, supported by a needle. It is easy, very easily rotates. And when it is exposed in the light, then it rotates like this. And if you put it in the sunlight, then it rotates very fast. You cannot count the rotation. And so why it rotates? There are two tricks. Number one is the air is pumped out. Therefore, the inside it's a low density gas, but not very much. Because if it is very vacuum, then this crashes. So it's a simple glass bulb. So it's not very high vacuum. So maybe the inside is 10 to the minus third to 10 to the minus fifth of atmospheric pressure. Therefore, the constant number inside is based on this vane is like 10 to the minus third to 0.1. So it is not very rarefied. So close to equilibrium. And also the second trick is that the one side of the vane is blackened, and the other side is not. So other side is reflecting. Okay? Then, so this is really the effect of gas rarefaction, or effect of microscales, which should be handled by the Boltzmann equation. And this is really classical phenomenon, and many important scientists consider this problem. And more recently, it has been a hot topic in microfluidics because one can, it's a potential mechanism to make a small, very tiny motor. And in fact, last year there was an international symposium on rarefied gas dynamics in Zaragoza, in Spain. So there are 4 or 5 papers on this subject. And so usual explanation of this effect is if you put this vane in the light, then black side absorbs radiation, so it is heated. So there is a temperature difference between two surfaces. This surface cold and the other surface hot. And the molecules hitting the hot surface are reflected after gaining energy on this hot surface. So it is faster. So this this has more energy and more momentum. Therefore, the reaction of the momentum, you have a force like this. So this is the usual explanation. And this is really the low density gas flows caused by temperature difference and the resulting force acting on the vanes. So this is a good subject of kinetic theory. And so we considered a very simple model for that. So we consider a thin plate, infinitely thin plate in a two-dimensional box. So this is only the problem is 2D square box and thin plate here. And the one side of the plate is kept at the same temperature as the temperature of the boundary, but the other side is heated to T1. Then what happens? What is the flow? And what about the force acting on the plate? Okay? And so this is not an easy problem because there is a discontinuous wall temperature. So this introduces singularity in the solution of the Boltzmann equation. And also there is sharp edge. So this also introduces the singularity, more precisely discontinuity in the velocity distribution function in the gas. So we tried to solve this problem using a simple VGK model and arbitrary constant number and under the diffuse reflection boundary condition on the surface of the container and the plate. Then we perform numerical analysis by finite difference method. But some years ago we developed a very accurate numerical method, which is not efficient, but accurate numerical method to describe this singularity. Let me just show the result. I omit all the complicated numerical schemes. And this is the induced gas flow in the upper half because it is symmetric. So this shows this part. And when the temperature difference is 2, so it's a temperature difference is very large to exaggerate the flow. And then L over D is 4, it means that the side of the square box is 4 times of the width of the plate. Then this first quadrant and second quadrant are a little bit separated here to show that the flow velocity on the surface. Okay? So it is a bit separated, but it is in contact in reality. And when the constant number is 5, these arrows indicate the dimensionless vector in x2, x1, x1, x2 plane, and this is dimensionless, and this is the length, the scale. So it is very small. And when constant number is 5, very rarefied, you see some vortex here, and as constant number is decreased, the induced flow becomes large because this is 0.05, but the flow is more and more localized. So you don't see the flow in the bulk of the gas. So therefore I try to magnify. So I magnify this part to see the flow structure. Then the constant number is 5. This is a long mean-free path, 5 times over this plate. So you see this side almost uniform flow is observed like this. But when the constant number is decreased and the gas approaches the continuum limit, then see there is the curved flow from this side to this side, and also even in this magnified figure near the edge, still it's localized. Okay. So this is a temperature field, and in particular this is impressive, this small constant number. You see the isolines concentrate on the tip. So this is because of the singularity caused by the discontinuity of the temperature, and also the singularity caused by the sharp edge. So here the temperature is not uniquely defined. So this structure can be described only with a very accurate numerical scheme which can describe the discontinuity in the solution of the Boltzmann equation. So I skip And also we can compute the force acting on the plate as a function of the Kusen number. So this is in this case. The temperature ratio is 2, and this size of the box is 4 times of the width of the plate. So, so in this normalization, when the Kusen number goes to infinity, then this goes to a finite value. It is a bit misleading. So here, the normalization is done by the average density of a gas. So if you increase the constant number, keeping the size of the box fixed, then also this goes to 0. Therefore, if you plot the dimensional flow, dimensional force acting on the plate as a constant number, then there is a peak somewhere between 0.1 and 1. Okay? So then when the constant number goes to infinity, then the force goes to 0. And so this is a normal stress on the plate. So P11 plus is a force acting on the plate from the light, like this, per unit area. And P11 minus is normal stress acting on the left surface. And so the difference gives the force acting on the unit area of the plate. So this is plotted in this figure. And this 0 is the center of the plate, and 0.5 is the edge. So from center to the edge, and when the constant number is large, then the force is uniform, completely uniform. But when the constant number is 1, still uniform, but as the constant number decreases, then dramatically the central part, the force decreases to 0, and then you have a force only at the edge. Okay, so most of the bulk of the plate, you don't have a force. Only in the edge, you can have a force. So when the constant number is 0.01, this is the case of real radiometer, the edge is very important. Okay? And so the usual physical explanation is as I said, the molecules hitting the hot surface gain energy, and also then it becomes faster. So and the reaction gives the force in that direction. This is usual explanation. And it is correct when there is no collision. Yeah? So in fact, this case, or even this case, the collision is very few. This explains the mechanism. But what happens when the collisions are frequent? Then, so it is true, it is the same that reflected molecules are faster. But these fast molecules, very energetic molecules, kicks out the incident molecules. Therefore, number of incident molecules is reduced by this. Therefore, the impact is reduced. So you don't know. And maybe this balances this, and so you don't have, you can imagine that there is no force in that case. In fact, it is true. In the middle of this case, this happens, so there is no force here. But if you go to the edge, then again the energetic particle kicks out the incident molecules. But there are incident molecules from side. So therefore, the incident molecules from the side, the reduction of the incident molecules by this kicking out effect is compensated by the molecules coming from the side. So then this close to the edge, the usual explanation is more or less true. Then the force acts on there. So edge effect is important when the constant number is relatively small. And also we wanted to simulate this moving plate problem, but it is difficult. And so because we are using very precise numerical methods of describing singularities, in that case many singularities comes out. So then we considered a simple model. Just I cut here, then I make it linear. Then this means that there is infinitely many plates, an array of plates moving in the channel because of this temperature difference. If you give a temperature difference, then it moves. in the channel like this. So it's a model, simple model. And then the good point is that in this problem, if you are sitting on the plate, then the walls, two walls are moving like this. It's a completely time-independent, steady problem, not a time-dependent problem. And in addition, you can impose a periodic boundary condition here. So this problem is almost the same as previous one. So we can easily solve this problem. And then we change the velocity of the of the wall. Then at some point, the force due to the temperature difference is balanced by the drag force given by the motion of the gas, induced by the motion of the boundary. So then at some point, you can get this speed of the boundary such that the net force acting on the plate is zero. So this means that with this velocity, this moves steadily. So in that way, we can compute the motion, velocity of the motion of these arrays. And so we computed some velocity of the motion of arrays, the different temperature ratios and different geometries. As Kunsei number goes small, then like it decreases. But this is not a real situation. And now some people are doing the simulation of moving vanes, really. Unfortunately, we are not able to do because we stick to the very precise description of the singularity, etc. But other people don't care. So, for instance, so the people from Bordeaux in France, Guillaume de Clistet and Luc Mussens computed recently the moving vanes in radiometer. And Guillaume de Clistet was in Kyoto in my group for 1 month. He's still in Kyoto. I left him in Kyoto. So he gave me the videos, the movie, that I will show this. So actually, this is not mine. So it's nice. This is difficult problem, moving boundary. Now, the moving boundary problem is in fashion in kinetic theory. And of course, it's not very accurate because, I repeat, it should be steady state, but you see there's some fluctuation of the temperature here. So it's in that sense, it is not very accurate. But anyway, you can see the moving vanes. And also he compared his result to our result of this problem. So we fixed the plate and then we changed the boundary, the velocity of the boundary. But he computed the really moving plates. And he compared with our result, and the agreement was quite good. So that method is very powerful. It's they call this. It's a finite volume method and a cut cell method, and he uses locally moving mesh. Okay. Finally, I must say a few words about my supervisors. And so my research career has been supported by many people, the supervisors, teachers, colleagues, collaborators, and students. And on this occasion, I would like to thank all of them. And in particular, my special thanks are due to Professor Yoshio Sone and the late Professor Carlo Celciniani. Yoshio Sone was my supervisor from the time of master thesis and also a PhD. And then I joined his group, and I was in charge of the separate group in 1994. But since before that, I was in his group, and then after that, we very much jointly worked. And so I learned many things from him. And but I was in Milano as a kind of researcher, both sister, for 2 years, long time ago, from 81 to 83, working with Carlo Cialciniani. So I learned a lot from Carlo Cialciniani. And after that also we have kept a good relationship, and sometimes we worked together. And unfortunately he passed away in 2010. And, so this photo I took 1983. So he was 44 years old. And now this photo is rather famous. So because Cedric Villani used this photo for the poster of the conference dedicated to Carlo Cialciniani in 2011 in Paris. So now in the internet you can easily find this photo. Okay, I think it's time. Okay, I stop here. Okay, thank you very much for your attention.
Thank you very much for your lecture. Some question, comment? Few minutes for the discussion. Just a question. In the recipe, they say that the radiometer is a proof of the energy of the photon.
It is not correct.
It is not the main thermodynamical part.
Yeah, it's yes.
You worked on this point. The effect of the energy of the photons are important. Is it possible to see or not?
I don't know, but I think there are some. I don't remember who was, but there was an experiment to confirm that this is not the effect of photon energy. So there was an experiment which showed that it is not correct. I don't remember now.
If you put in the vacuum, there is no movement. You should put the vacuum.
Yes.
In the vacuum would be the colors, otherwise we can't.
Yes.
If you realize a really real vacuum it's very difficult.
Yes. So if it's very rarefied, the effect decreases in a sense.
And to keep
Just one question.
Yeah.
Do you know if there is a continuum modeling of this turning effect?
Yeah.
Using the basic kinetic energy?
Yeah, of course, when as I said, the constant number is small. Therefore, the most of the gas is described by fluid dynamic equations. But you have to use the correct boundary condition, the strict boundary condition. And if the temperature variation is smooth from hot to cold, then it is possible. But if there is a sharp change of the sharp edge or sharp change of the temperature, like discontinuous change, then you don't know the boundary condition for the fluid equation. So you have to use the kinetic theory.